Hello, hello, hello. Welcome. This is Algebra 2. It's May 11th. Class Connect number 7. How we doing today? Thumbs up, sideways, down. Okay. Not too shabby. Always a good thing. So we've kind of been working, I would say almost this last month on exponential and logarithmic functions. And this is kind of the recap of it. So we didn't actually learn anything new this week. This was review and kind of preparing and practicing to get ready for your test. So I'll run through kind of just broad, big, general idea topics, and then just gonna let you guys kind of practice. And if there's problems we want to do together, or if you have questions, as I'm going through anything, please jump in and say something. So I was kind of looking, and again, kind of found something like this. I just thought this is a good way to just go through and look at, again, what does an exponential growth function look like? The parent function. What does an exponential decay function look like? Domain and range, okay? I'm almost always asking that you include those when you graph stuff. Okay, again, this is one way to write it, but really what I need a lot of us to work on is labeling our asymptotes. So like you would want to say that this is the line y equals 0. Y equals 0 is a horizontal line. So you have to kind of label your asymptotes. And like when we get to a problem, say there's like a vertical shift where now my asymptote is y equals -2. Okay, this is y equals -2. Some of us are writing the range. We're just saying like y equals -2. Okay, that's not how we write range. If you want to say it like that, you would have to say y is greater than -2. Okay, that's how you would include the range in this example. So anytime you have intercepts like this, okay, if you're graphing a function, you've got to label your x-intercepts if it crosses the x-axis and any y-intercepts if it crosses the y-axis. That's just sort of best practices for when you are graphing sort of anything. Okay, so again, growth, decay, move left or right, move up or down, reflection. Look what happens. We've got this negative sign, is how it creates a reflection. And in our exponent, it reflects it again a different way over a vertical line. So the inverse of a logarithmic function is the exponential function, and vice versa. The inverse of an exponential is a logarithmic function. And the inverse of a function is reflected over the line y equals x. So again, if this is our graph y equals 2 to the x, we're again pretty comfortable with exponentials. Well, then my inverse is going to be flipped over this line, and this is going to be log base 2 of x. So again, I have a conversion technique where I can move from exponential to logarithmic and vice versa. So just kind of looking at how these are related to each other. Kind of the same deal, okay? We can do horizontal shifts by, if we look right here, affecting the number that's inside of our log, inside of our parentheses. Again, subtracting 1 moves it to the right one. Vertical shifts, again, doing something outside of the log, which is again very similar to the exponential function. This moves it up 2 units. And then reflections, again, using that power of that negative to either reflect it over a horizontal log when it's out here, or reflect it over a vertical asymptote when it's inside of my parentheses. So those, again, are kind of the big ideas regarding transformations. One of the most, I would say, useful parts of this idea is getting the natural log base E, which again approximates to about 2.718. and we use that for continuously compounding interest. So we've got this formula. I know that we will at least practice one of these, which again, when it compounds a certain amount of times per year. So it could be monthly, it could be daily, it could be quarterly. So it's not continuous. And then here's our continuous formula. So really useful. Again, I try to give these to you in the problems, but definitely make sure you've got notes on how to do these, and you can use these formulas. You cannot take the log of a negative number. Again, if we look at sort of my functions, okay, there's nothing, there's an asymptote here. There is nothing happening on my negative side until I try to reflect it. So keep that in mind. Log has a base 10. So again, in our calculator, whenever we use a log, it's in base 10. We do have a formula to convert it if it's not. Some calculators can just do it naturally. Again, natural logs, ln of x, it's log with a base e of x. That's the natural log. We just shorten it to ln. Common properties, again, we know these cancel each other out. When you have the same base of your log and the base number, they cancel each other out as well. Works vice versa. Change of base formula. Again, I know I'm going through this fast because this week is review. We have spent the last 3 weeks kind of going over this stuff. Being able to expand or compress our logarithms, again, being able to manipulate them, you're going to be asked to do that. So make sure you can do that. I think we practiced that last week. And again, real quick, before we get into our practice, here's just a couple more examples of some of those situations. I guess just a different way of looking at it, a different way of kind of explaining how these work. I think I might post this as well on Schoology. So again, if you want to take a look at this afterwards, you're more than welcome to. Okay. Real fast overview recap. Any questions? Anything you didn't get a jot down or anything before we get into solving some of these for practice? Copy. All right, sweet. Here you go. There's your link. We've got 6 people today. All right, I'm going to share my screen and just share the questions if you are watching the recording. Rewrite. And rewrite this, rewrite this. All right. Kaylin, woohoo, doing great. Okay, let's do about 3 more minutes of this because there's a couple other types of problems I want to do as well. So about 3 more minutes of this individual practice. All right, finish the question that you're on. We're gonna do a compound interest problem question after this, but finish the one that you're on. Great job overall as a class. We did really, really well. So that's awesome. Okay, awesome job. So I'm gonna pull up the question, and then I want you to kind of try it on your own. Oops. Stop. We're not there yet. Okay, here's the question. An investment earns 3% each year and is compounded monthly. Calculate the total value after 6 years from an initial investment of $5,000. So I'm going to first get the formula. Okay, the formula is A equals P parentheses 1 plus R divided by N, close your parentheses, N to the T power. And I'll share this. Okay. Oops, wrong thing. All right, let's take a look. So, my initial investment was $5,000. So that's going to be P. Uh, R was my rate. It earned 3%. So just remember, percents you got to turn into a decimal, and 3% is 0.03. So 0.03 is 3% as a decimal. So 1 plus 0.03. N stands for how many times it's compounded per month or per term or whatever. And this says compounded monthly, which gives me 12. And then N, we just said was 12. And then my time was 45 years. So after 45 years. So I'm going to simplify some of this. Let's see if we can get 0.03 divided by 12 a little bit more simplified. So that equals 1 plus 0.0025. And then let's do 12 times 45 as well, which is 540. So now I'm almost ready. I can do one more thing. There. This is what I want to plug into my calculator. 5,000 times 1.0025 to the 540th power. And why did I say 45, Mr. Larson? That is so not correct. It's after 6 years. Wow. I know why I did it. You'll find out in a second, but 6 for our time. 12 times 6 is 72. 72. Wow. Okay. I was like, that number is way off. 5,000 times 1.0025 to the 72nd power. And I get $5,984, and we'll round that to 74 cents. All right. Let's look at the Class Connect assignment. Autumn, I did send you a message in the chat if you want to just read that for a sec. Otherwise, let's go look at our Class Connect. Again, you can find it at the top here. Class Connect assignments folder. If you had trouble last week, okay, there was a hard question about mice last week. If you look in the updates, I kind of go over it. And again, why it's tricky is because you almost have to find the rate twice. So you have to go through our equation just to get R, and then you have to do that again. Don't round this. So that was one problem I found with the student. They were getting this as a decimal and rounding it. Keep this number in this natural log of 6 divided by 2 form, because that's going to give you your most accurate answer. Okay. That was a correction from last week. So if we look at our assignments, we just practiced one of these. This one's slightly different because they say that we want to have 2 million for retirement. This is where I got that 45 number from. Pays 8.5% per year, compounded quarterly. So there's 4 quarters in a year. This time we're trying to find the P initial investment. So again, our end goal is $2 million. So I'm going to put that over here. I'm going to put that for A. P is what I'm trying to find. 1 plus my R, my rate, it said 8.5%. So again, 8.5% as a decimal is 0.085. And it's compounded quarterly, which means divide by 4. And then my N value, we just said was 4. Let me move this a little bit. And then time we said was 45 years. So let's start simplifying. Again, I don't know P. 0.085 divided by 4 is 0.02125. So 1.02125. And then 4 times 45 is 180. I still have 2 million here. I'm going to go ahead and calculate this number right here. 1.02125 to the 180th power It's going to give me P multiplied by 44.0324162. Again, I don't really want to round it right now, but I'm going to divide this out on both sides. Okay, I'm going to divide this over here as well. 44.0324162. So 1, 2, 3, 4, 5, 6. Make sure you got enough zeros. And I'm going to get about $45,421. And let's round this to 0.08 for my P. So that's how much I initially invested. And if we look, or that's how much I would have to initially invest in order for 45 years to have $2 million. Very common sort of retirement planning deal. Okay, couple problems here. Again, real quick, using your properties of logs, I'll set it up for you and then you can most likely finish it. Natural log of x plus 1 equals 1.86. Natural log and e are kind of like inverses. So what I'm going to do is I'm going to raise both of these up and have a power of e so that this cancels out and I'm left with x plus 1 equals e.186. So subtract 1, and that's going to give you your answer. And then the second question, and again, the directions say to round to 2 decimal places. So I get x equals 5.42. And then the second one's, I'd say, even a little bit easier. It's E 9.8 divided by E 7.6. Well, this could be rewritten like this. And then I know that when I have something like this, division in my exponents, I can just subtract them. So what's left? 2.2. Find out what E to the 2.2 power is. And round that to 2 decimal points. So I got x equals 9.03. Okay, that is your two of them are the same. Never mind, I read it wrong. Okay. Yeah, it is kind of confusing. They both have x in there. Maybe I can switch that up, make it a little more clear. That's your assignment. Good luck. Again, study hard before you take your test. Let me know if you have any questions. Ask the questions before you take the test, so you don't make the same mistakes.